Puede ser en inglés si quieres, ha estado muy bien.
Sí, si quiero ser amable, está bien, perfecto.
Sí, perfecto.
Te pido.
Muy bien, antes de comenzar, déjame presentarte, Eric. Entonces, egresado de la Universidad Veracruzana, igualmente obtuvo el doctorado del Instituto de Física de aquí en San Luis Potosí, y también uno de los primeros egresados del grupo del profesor Jürgen, del cual es esta fiesta. Él estuvo también en Ontario, Canadá, haciendo un postdoc, y actualmente trabaja en el Instituto de Física de la UNAM, y además de haber sido reconocido también por la cátedra Mushinsky en el 2020. Adelante, Eric, por favor.
Muchas gracias, Elías. Okay, I'm going to give my talk in English. Let me share my screen. I'm gonna need to share sound because I have some videos and I'm trying to. Okay, can you see my slides?
Yes.
Okay, excellent. Okay, so this is the title of my talk, Search for Sevens in Reactors and Galactic Dark Matter using with liquid argon. I only have actually one picture of my time in San Luis Potosí with Jürgen. I just found it online today because I don't have any other. As Ibrahim said, it was those times where we didn't have cameras in our phones. And I don't have, I basically don't have any. So I hope that I asked Nora for a few pictures. So I hope I will get some to share for when we meet. Okay, so first, just a brief introduction about, I want to do this first before my talk. So I met Jürgen in 1999. I went to San Luis Potosí to this contest for the summer student program in foreign laboratories. I was awarded actually one of the places, and I went to DESI in the summer of 2000. And before leaving San Luis Potosí, I talked to Jürgen, and he told me that I could go and do my graduate studies with him. So when I returned from Germany in the summer, I worked as a technician in his laboratory, and that was from 2000 to mid-2001 until I could go to the graduate program in San Luis Potosí. And actually, that position is now held by Luz, who is also present here. And I started my PhD in 2001. The first day was on 9/11 in 2001. And I did my PhD in sharp baryons in Selex. And at the end, I will mention a brief some of the stories that I remember from San Luis Potosí and all that time. And I finished in 2008. And then for the next 14 years, I switched fields. And I'm going to tell you what I work now. And then at the end, I'm going to talk a little bit more about what I call the legacy that I have from Jürgen. Okay, so now regarding my talk, my interest, my area, the area where I work is in dark matter and neutrino physics. This is just a brief introduction that I'm going to present about the physics that I do, because it's slightly different from what I did with Jürgen. When I was working with Jürgen, low energy particle was a 15 GeV pion. And for me now, low energy, it's a few EV or even a few KV. So this is the pie chart of the universe, where I show the contents of the universe, where we know that the matter that we know, the standard model particles, is about 5%, and there is a 95%, which is split into 69% called dark energy, and about 29% dark matter. And this is the field where I work. I do experiments on direct detection for dark matter. And this is a slide that I always like to show. I'm going to just flash some of these slides quickly. I think that I failed as Ibrahim to spend 1 minute per slide. Although I still tell that to my students that they should do that. So this is basically all the evidence that we have. It's an impressive and overwhelming number of observations on different scales. We have the very well-known rotation curves of galaxies. We have galaxy emission of X-rays in galaxy clusters, and also gravitational lensing. So all this evidence points towards an unknown amount of matter in the universe. And on the other hand, we also have our current best model, lambda CDM, and where we have evidence from the CMB, from the cosmic microwave background. Going into precision cosmology, we also have abundance of primordial elements. That's usually combined with predictions from nucleosynthesis from the Big Bang. And also we have structure formation. So basically simulations at large scale in the universe. So all these points to this unknown type of matter. And there are many possibilities, some even modifying the laws of nature, like gravity or relativity. The evidence also it points in favor of a particle, and there are several evidences or possibilities, models that could point to this dark matter. So what we know about dark matter basically is what we don't know about what dark matter cannot be. And we know that it is interacts gravitationally. It is stable and or long-lived. It has to be cold or warm. It cannot be any of the particles here in the standard model. It has to be electrically neutral, and no color, and it interacts very weakly. So this calls for physics beyond the standard model. And this, again, I show a range of possibilities of masses and candidates. At some point, the neutrino was a candidate, but it was ruled out because it is relativistic. And axions, we have also WIMPs, which is the field where I work. And this is basically one of the most discussed candidates. It's a particle that very likely was produced during the Big Bang in thermal equilibrium in the early universe. And basically, as the universe expands and cools down, these particles very rarely now interact with each other, and then they freeze. And they decouple from the ordinary matter. And there are still around some of them with densities of a few per liter, depending on the mass. And I know that a lot of people think about all these SUSY models coupled to that matter, but we don't know actually the coupling between the standard model and the dark sector. So, and the standard model is very rich, so it's very likely that this dark sector could be also very rich. So how do we detect these particles? So basically, we are looking for elastic scatters with nuclei. And this is a cartoon, basically, where we have a nuclei here, and then a dark matter particle will come, will interact here with the nucleus. There will be a recoil of a few keV, and that's what we measure. That's one of the ways that how we search for this dark matter. There are other possibilities also, indirect detection and production in colliders. Basically, that's what this is the area that I will present now. And then we basically calculate the rate based in some assumptions. And historically, we search for two types of couplings. One that we call a spin independent, which is just basically goes proportional to the number of protons and neutrons in the nucleus. And then one that we call spin dependent, that couples to the spin of the nucleus. And this is basically the cross section. And this is what we do. Basically, we have a differential rate of events, and we have four main components. First, we have the dark matter density component. We don't know the mass of the dark matter particle. Then we have the particle physics component here with the cross section, which is expressed from either a spin independent or spin dependent. Then the nuclear part, and finally the velocity distribution of dark matter in the galaxy, assuming a Maxwell-Boltzmann distribution and with some uncertainty. Then we put all this together. We don't know the cross section, we don't know the mass, and then what you usually see in these experiments is a plot of the WIMP nucleon cross section versus the WIMP mass. And here are some experiments that, regions that had been ruled out by some experiments, some models on possibilities for dark matter. And this is the coherent neutrino scattering from solar neutrinos, atmospheric and diffuse supernova neutrinos that at some point will be an irreducible background. So how to catch a WIMP? So basically we live in a dark matter halo. We have a local density of about this value. What we are looking for is for the coherent elastic scattering of the nuclei. The problem is that we have many backgrounds from natural radioactivity. These are neutrons, muons, beta decays, gammas, alpha decays, and even neutrinos. And basically, when we account for all these, we are talking about 10 to the 11, 10 to the 12 events per ton per year. And we need to reduce those because we are looking for, at this time, experiments are sensitive to 1 event per ton per year. So basically what we do is that we go underground, we shield the experiments, and we do a careful selection of the materials to avoid radioactive impurities or to minimize them. Besides that, that only gets us to probably 10 to the 7, 10 to the 6 or 8 reduction. We still need to develop another techniques to distinguish nuclear recoils from electronic recoils. And this is basically the receipt for direct detection of dark matter. We are basically looking for tiny energy deposits, basically recoils of, this is non-relativistic, so we are basically searching for a 50 keV nuclear recoils. And as I mentioned, the background suppression by going underground, by having a shielding and the careful choice and preparation of the materials. And these are just 3 examples. I'm not going to talk about this. I'm going to talk about this in the experiments that I will present. This is basically the background discrimination where we discriminate the electron recoils against the nuclear recoils. And then we just basically use large target masses. We scale our detectors to tons. Basically, that's the status of the experiments. So the experiments where I have been working are at SNOWLAB. This is the deepest and cleanest large space international facility in the world. It's 2 kilometers underground in Sudbury, Ontario. It's a very clean laboratory with a physics program focused on neutrino physics and dark matter. And here is the snow cavern. That's the home of the SNOWS experiment that in 2015 was awarded the Nobel Prize in physics. These are some pictures of the underground laboratory. Here is the entrance of the lab. And this is basically the areas, the halls, the caverns of the lab. Here is one of the experiments where I worked. And I spent 6 years there as a postdoc and 4 years as a postdoc and then 2 years as a research scientist. And basically everything you see here is clean at levels near what you find in a company where they fabricate our drops, right? That's basically the cleanliness. So the most radioactive place in the lab, it is this corner here. And that's the coffee machine. So coffee is basically the most radioactive thing that we have underground in the lab. Besides the calibration sources, right? I guess the cabinet with the calibration sources, that's the hottest, the most radioactive place in the lab, but second is this. I'm gonna, at the end, I probably, if I have time, I will present a video of the laboratory. I'm going to talk now about two experiments. One is Deep 3600 and the search that we do for dark matter using liquid argon. This is the collaboration in 2018 when they came to Mexico City to the Institute of Physics at UNAM. We are basically more than 80 researchers from Canada, Germany, Italy, Mexico, Russia, Spain, the UK, and US. And these are the participating, the collaborating institutions. In DEEP, we basically use liquid argon, and that's because argon is a scintillator. Basically, when nucleons are scattered, they are detected because of the scintillation light that they emit. And we use something that is called pulse shape discrimination to suppress beta and gamma events, basically electron recoils. And that's because when there are nuclear recoils in argon that produce dimers, and there are two different lifetimes for the two states, the argon singlet and triplet, and those are associated with electron recoils or nuclear recoils. And here you can see a pulse from an electron recoil, and here from a nuclear recoil at the bottom. And we define something called the F prompt, which is the fraction of light in a time window of 150 nanoseconds divided by the total PE. And that basically splits the electron recoils here at the bottom from the nuclear recoils, and that reduces our backgrounds. And we use argon because it's easy to purify. It has a high light yield. We started operating one detector as a prototype, Deep 1, which consisted of 7 kilograms. And now we have running Deep 3600. It's more than 3 tons. We actually have 3.3 tons of argon now, and we have 255 PMTs. This is the detector. We have here the acrylic vessel filled of liquid argon, and then we have the 255 PMTs separated by 50 centimeter light guides, also made of acrylic. We do this because the PMTs are the hottest components in the detector. They are made of borosilicate glass that produces lots of neutrons. So we need to keep them away from the detector, and also because they operate at room temperature. So this is cryogenic, and we have a gradient, a temperature gradient here. And all this detector is basically immersed in a water tank of 8 meters by 8 meters, 8 meters tall and 8 meters diameter. And this is basically how we built the acrylic vessel. It was made at RPT, Reynolds Polymers in Thailand. And then it was shipped in a boat to Canada in 4 pieces. So then they were put in an oven. And then this sphere was transported underground to Snow Lab. This has been up to date the largest object shipped underground. And this is when it reached the cavern. This is actually the water tank, and this is where we couple the neck of the detector. And this is a very nice pictures of the detector when we couple the light guides underground. Then we put some polyethylene and some other shielding, and that's nearly completed. You can see the back of the PMTs here. And of course, when you spend 10 years building a detector, so you get the National Geographic to go and take a picture because it looks impressive to have this detector. This is a picture, a very nice picture. And you also get to be on TV. There is a TV series on CBS, Scorpions. And so at some point, we noted that in some of the episodes, the characters in that series, they had to go to a lab underground. And that's because an experiment had claimed to detect dark matter, and the government wanted to be sure that it was correct, the claim, because the experiment was requesting lots of money, and the government needed to be sure. So they hired these detectives to investigate if it was correct. And we noted that they took the shape of our detector, and actually our PSD discrimination, it seems that they look for deep to make this episode. But anyway, I don't follow this series, but it was exciting to see the experiment on TV. I'm going to quickly just flash some of the details of the experiment. We had to actually sand to polish, we could say, our detector underground, and that's because contamination from the air that plays out in the surface of the acrylic, and that leaves lead-210 and polonium. But lead-210 is very complicated because it has a half-life of 20 years, more than 20 years, and we need to basically sand a few micrometers from the detector to remove these backgrounds. We have a very clear discrimination of the electromagnetic recoils and the nuclear recoils. As you can see here, these are the beta decays. This is the potassium 40, the 1.46 MeV line, thallium 208. And here we can see all the alphas, surface alphas in the detector. And here, very tiny, it's the WIMP region of interest. And this is basically our background model in the ER electronic recoil band. And these are some of the backgrounds. We also have very nice calibrations of the detector. Basically, we calibrate, this is the energy calibration and the number of photoelectrons detected for a few lines, natural lines as the potassium, bismuth, and thallium, and of course, sources as a sodium-22 source. Besides, the optical properties are studied with light injection using fibers. So we have a very well controlled, and we understand our detector very well. So we started construction in 2012. Basically, we begin the first field in 2016. We ran for 1 week, but then we have a seal failure in our detector. And then we began a second field in 2016. We finished in October 2017. I'm going to present some data that we basically analyzed and put out the results in 2019. And currently, the detector is empty. We are doing some upgrades, fixing this seal failure, and hopefully next year we are going to start filling it again and go for another search. So basically, this is what we found. We found 0 events in the region of interest. This is the region of interest, which is defined by these cuts. Basically, it is defined as a 1% nuclear recoil acceptance loss, a 0.05 electron recoil backgrounds, and this is kinematics from WIMPs, and then half neck alpha decays as backgrounds. We ran for 231 light days, and we had a fiducial mass of 824 kilograms. And this basically allows us to put these limits. This is the DEEP 3600 result. It's this work, and we are still not competitive with Panda X, with LOX, and with Xenon 1 ton, with the Xenon detectors in the spin-independent channel. And but we hopefully next year, when we have the full detector running for 3 years, we will be able to reach this space parameter region. We are slightly better in some isoscaling violation scenarios. I'm not going to present these. I'm going to briefly just to talk about, because that's related to the work that we do at IF. This is DEEP. This is the detector. As you can see here is with the light guides with the PMTs. And this is how it looks like now, the detector with the water tank empty. And we are about to, or we are doing the upgrades in the detector. So this is one of the experiments. This is basically the search for dark matter using argon. And this is the first part of my talk. And the second part, I want to talk about the SBC, the scintillating bubble chamber. This is a 10-kilogram liquid argon bubble chamber for dark matter and sevens. And this basically, I'm going to talk briefly about reactor neutrinos through sevens. And in order to detect these, this is basically the sevens process, as you can see here, to the via the Z0 boson. And basically, due to the coherence, we have energies, we need energies of the neutrinos of roughly, we could say 10, 50 MeVs, and that gives us nuclear recoils of 50 kVs, which is basically what we do in the search for dark matter. So we basically need, as in a dark matter detector, a very low threshold and recoils of a few kV. And this process that was observed for the first time by the coherent collaboration in 2017 has a high cross-section compared to the inverse beta decay. So basically, that's something very good. We need to go to low thresholds and even do an event-by-event discrimination, but fortunately, the cross-section is very large. So, so basically, we just need to put one of these dark matter detectors, similar to those, near a nuclear reactor to search for this process. This was measured in the expallation source. Basically, nobody has observed coherent near these coherent interactions near a reactor, and that's what one of the parts of the physics program that we are aiming for in the SVC collaboration. But first, let me talk about bubble chambers, just to present in what is based what this work is based on. This is the PICO collaboration. And this is the time when they were here in Mexico City in 2016, and at the Institute of Physics. This is the collaboration, and we were discussing earlier, right, about this visit with Peter Cooper, and all this came to Mexico for the collaboration meeting. And basically, we use bubble chambers, not the typical bubble chambers used in the 70s in the particle physics experiments. This is slightly different. And we basically have a synthetic quartz jar, which is filled with a liquid. We usually use these liquids, CF3I, C3F8, and that's basically because we are aiming to search for spin-dependent interactions through fluorine, which has spin. And then this jar, this quartz jar, is immersed in a stainless steel pressure vessel filled with an hydraulic fluid. And this is connected basically to a piston. Well, lately it's slightly different, the system, but basically the idea is that when particles come, this liquid is in a superheated state, and when particles interact, they evaporate a small amount of material that produces a bubble. And we have 4 cameras that take pictures of these bubbles. And then we have acoustic piezoelectric sensors that detect the sound, the pop, when the bubble is produced. And at that time, basically, what we do is to compress the system to about 200 PSI to basically recondense the fluids. And then we expand the detector after a few seconds, basically to leave it again in a superheated state. And this is working in cycles like these that you can see in this sketch. Basically, there are recompressions after each event. And basically, the physics behind this is just a competition between the surface energy and the latent heat. And everything, this is basically explained by the sites model, the hot spike model. And the production of bubbles, basically, the nucleation depends on the energy and the stopping power. And this is very interesting because since it only depends on the stopping power, that means that there are some particles that even having high energy, they cannot produce bubbles. And this is basically in this diagram, I have the stopping power and the energy and the region where we can nucleate bubbles. And basically the electrons, even having enough energy, they don't deposit the energy within a critical radius to nucleate bubbles. What produces bubbles are the alpha decays and the nuclear recoils from carbon, fluorine, or iodine, according to the elements that we use. So basically, these detectors are insensitive to electrons and gammas. This has been measured in situ with calibration chambers and also with our detectors. And this is basically the energy threshold at which we operate the detectors and the probability of nucleation from electron recoils. And this is for C3F8 and for CF3I. And these detectors are sensitive to basically, if we remove their insensitivity to electrons and gammas, to alpha decays, to neutrons, and to WIMPs. And these are basically events from a neutron calibration source. Neutrons are very special because they produce one or more than one bubbles, and that's because the mean free path of the neutrons in these fluids is about a few centimeters. So we get to measure neutrons by their multiplicity, multiple to single ratio. And alpha decays are nuclear recoils and the alpha tracks, and they produce only one bubble. And of course, we expect that WIMPs produce one bubble. And so this basically allows to measure neutrons, to observe neutrons in our detectors. And then we only have to discriminate alpha decays from WIMPs. And alphas are very interesting because they are basically a nuclear recoil and the 40 micrometers length that the alpha travels. And it happens that these are louders. You can think about that the nuclear recoil produces one acoustic signal, and the alpha decay consists of the nuclear recoil and the alpha track. So that signal is louder, we could say. And this was discovered by the Picasso collaboration. And you can actually see the acoustic parameter where we can differentiate two regions. These are the single recoils produced by neutrons, single nuclear recoils produced by a neutron source, an ambi source actually. And then in black and in red, you can see the alpha decays. Actually, this is alpha calorimeter because we can observe two signals from two different alpha energies. There are actually three from the uranium and thorium chains. And these are the acoustic signals from the neutrons and from the alphas, and we can discriminate these very well in our detectors. One thing about these detectors is that they are energy threshold detectors, so we cannot know the energy on an event-by-event basis. We do the usual background suppression by going underground, by water shielding our detectors. Basically, we have a shielding around the detectors and clean materials. And then the backgrounds, the alphas are discriminated by the acoustic parameters, while the neutrons by the multiple bubbles that they produce. And we have been operating different detectors on underground at SNOLAB. We are actually now building a ton scale detector, which is Pico 500. We use bubble chambers because these are zero background, basically. We can scale our experiments very easy. And we can have low energy thresholds depending on the fluids. And we actually can use different targets. And actually the SBC is based on an argon detector that I will explain briefly. And in terms of search for dark matter, we basically have different possibilities. This is under an effective field theory framework where we have different operators that go into the interaction that depend on the spin, on the transfer momentum, or the velocity of the particle. And basically, this is for the different elements. And as you can see for fluorine, these are sensitive to spin dependent, which are these two terms in this effective field theory. And by switching to different fluids, we can basically have study other interactions, and we need other thresholds. These are some pictures of our detectors. This is basically the quartz jar. Here are the acoustic sensors that we had in Pico 60. Actually, during my postdoc position, 3 scientists, I was one of them, were in charge of building this detector underground at SNOLAB. 2 from Fermilab, Hugh Lippincott and Andrew Sonnenschein. And this is actually the day that we put this jar inside of the pressure vessel that you can see here. And this is the detector inside of the water tank. This is how the pressure vessel look like. These are the viewports for the 4 cameras that you can see here. These are the LEDs to illuminate our detectors. And here's another picture. I like to put this because I am this one. You cannot see my face, but because I'm facing the detector, but I'm here during the construction of the detector. So we have, after more than 10 years at SNOLAB, we have produced world-leading limits in the search for dark matter through spin-dependent wind-proton couplings. These are our latest results, where basically we are even more competitive than indirect detection experiments. We actually have a limit combined with IceCube. but these are from the results from our run in 2019, where we reached this sensitivity of roughly 10 to the negative 40, 10 to slightly better than that for wind masses between 10 and 30 GeVs. And these are basically the results that we have produced. So this is basically the experiment. This is the PICO experiment at SNOWLAB. And after this, well, continuing with this OXEX program, fraction of the collaboration led by Eric Dahl at Northwestern University decided to endure in a new experiment that it is called now the SBC collaboration. It's a small fraction of people. Actually, this picture is from 2019. So I need to update it from our latest collaboration meeting. We have doubled the amount of people here. The collaboration consists of institutions from the US, Canada, and UNAM in Mexico. And the idea is to develop one of these bubble chambers, but using liquid argon, basically combine what we can do with DEEP with what we can do with the PICO bubble chambers. And that's because then now we have 3 channels. We have the acoustic signal, we have the images of the bubbles, and we also have scintillation signal. And Eric's Dahl group started developing first a xenon bubble chamber at Northwestern that operated at a threshold of 900 EV. It was only a 30-gram target. And after the creation of the SBC collaboration, so the idea is to develop an argon bubble chamber with a threshold of 40 electron EV. And the aim is to have a 10-kilogram detector to also detect basically the scintillation light from the argon. Here are some pictures from the xenon bubble chamber that developed at Northwestern University. And of course, that's because Eric Dahl observed that basically there is an outstanding electron recoil discrimination for xenon. And so this chamber was exploring thresholds down to 900 EV and no gamma-induced electron recoils observed. And of course, this was observed years ago by Glasser. When he developed bubble chambers, he had actually to spike the bubble chambers to observe electron recoils. So it was the rejection, the probability to produce electron recoils is very low, and this is suitable for dark matter searches and for sevens. This is basically the detector, basically 10 kilograms of liquid argon spiked with a few ppm of xenon. With the CPMs immersed in the hydraulic fluid, which is CF4, operating at these cycles. And this is basically the CAD model of the detector, which is being commissioned right now in Fermilab. Actually, unfortunately, I didn't have time to put some pictures that we have recently from last week, but I can share with you if you are interested for this, the development of this detector. Basically, the vessels, they are ready. There is the design of the PNID for the fluids and the controls. The scintillation detection system is under design and fabrication. And basically, it's assembly operations on surface at Fermilab, and calibration will go from 2019 up to 2022, actually. It's extending until next year due to the COVID situation. What's the physics that we can do? Well, there are 2 possibilities. We can go for dark matter. We actually will have 2 detectors. One will go underground to SNOWLAB to do a search for dark matter at low wind masses between 1 and 10 GeV. This is for a target mass of 5 kilograms, 5 kilogram year. These are the limits competitive with super CDMS. And what I will talk is about sevens, basically to study, to search for sevens near a nuclear reactor. And once the current detector being commissioned at Fermilab is finished, it will be moved near to a reactor where we will search for sevens. And we are exploring 2 possibilities. One is, and both are in Mexico. One is a 1 megawatt research reactor at Inin, near Mexico City. And the other is in Laguna Verde. It's a power reactor in the East Coast in Mexico. So this is basically the physics. I'm nearly finished with this, with my talk. And this is basically, I'm gonna present 3 studies that we did for the reach of this detector. And basically, by measuring coherent, we will be sensitive to the weak mixing angle, the Weinberg angle. And this setup A, it's Inin, a 1 megawatt reactor. Setup B would be Laguna Verde. And this would be a similar reactor to Laguna Verde, but where we actually measured very precise the neutrino energy spectrum. So we basically will be competitive with atomic parity violation experiments. We also will be able to be sensitive to Z prime bosons. When we study these scenarios of V minus L gauge theories, where a new mediator appears. So we will be better than coherent, and we will be competitive with beam dump experiments in some space parameter, and of course, also with Atlas and LHCb and Babar, where we will be sensitive to study and to search for these interactions. Apologies, I missed the citation for this paper. Actually, it was accepted last month, and it is published now in PRD. We also will be sensitive to the neutrino magnetic moment. These are basically the results from coherent using the cesium iodine crystal and the liquid argon detector. And in our case, the 3 scenarios, Inin, Laguna Verde, will be as sensitive as Borexino and Gemma. So we will also have the possibility to study the muon magnetic moment with this scintillating bubble chamber. I forgot to mention that this at Inin is a 10 kilogram detector, and at Laguna Verde is a 100 kilogram detector. So, but that will be the physics reach that we will have. So basically, this is the work that I developed now. I switched completely fields, I would say. I guess that the only thing that we share are the PMTs and the Cherenkov light, I guess. You will say something else, right, Jürgen? Okay. And just to finish my talk, I was thinking, well, I know that in the morning there were a few collaborators that explained that talk about all the what is to work with Jürgen as colleagues, right? And it was very exciting actually to learn many things about Jürgen's early career, and I knew a bit about that. So I guess what I wanted to share is what I remember about my time in San Luis Potosí with Jürgen. What a great experience was to work with him and have my PhD in San Luis Potosí. I shared what Ibrahim talked about, all that. Actually, I had forgotten about some of them. They are too familiar to me, like 1 minute for a slide. I always tell that to my students. And then Ibrahim reminded me that I learned that from Jürgen. So I remember now that it came from you, but it's just natural in my scientific life now. So the one thing that I remember that I actually share with Jürgen, and I learned from him, it's just basically to discuss physics with as much excitement as he does it. So you probably noted it with my talk now that I try to explain a lot. That's what Jürgen does. It just basically, I remember sometimes when I was doing my PhD that I just wanted the answer for one question, and Jürgen used to tell me a story behind that answer. And now I do the same with my students. I mean, all that passion to explain what you know about an experiment or a physics result is actually what I share. 2 or 3 years ago, we met in León, Guanajuato for the particles and physics, the meeting of the division. And one of my colleagues told me that the resemblance with how I talk and I explain everything with Jürgen was scary. That's what he told me. So this is some of the passion that I share that I learned from Jürgen. Of course, as we were talking in the morning, I also teach with Prof. I learned that from Jürgen. Also, I always look for a correct calculation of the uncertainties with my students. And that's something that with Jürgen, we always discuss about that. One of the other things that I remember playing football and softball with Los Neutrinos, all afternoons that we used to play. I actually went to Snow Lab and I founded a football team as well. But instead of Los Neutrinos, because that name was taken, it was called Los Neutralinos, the Neutralinos. So, and I remember having a great time sharing some experiences. I mean, playing football and softball outside of my my PhD with Jürgen. I also one of the things that I learned from Jürgen, I also still use LaTeX and Emacs. Actually, this talk was made with a template from 1999 that Jürgen gave me for my, let's say, first official talk in a seminar, in a conference. And my students come and go, and they start using this keynote and all that stuff. I tell them that I will not put my hands in any of that, of those. I still use LaTeX and, of course, Emacs. And I compile my talks every time that I give one. I also have this feeling against, I guess, Windows. I don't know if I use such a strong words by saying hating Windows, but I remember this one time when I was the technician at the laboratory with Jürgen, and I was just came from my university, and I used to use Windows, and then after half a morning, Jürgen came around lunch. And I told him, look, I made a partition and I installed Windows in this computer and Linux at the same time. So when I say hate, it's because I still remember when he basically looked at me and said, delete that. I don't want that. Delete it now. Now, he told me that. And that's what I had to do, of course. And I guess that was, now I actually have to use some Windows because there are some National Instruments controllers that I cannot use Linux, so I had to go there. But every time that I start Windows, I remember that time in the laboratory. And of course, speaking loud, very loud and enthusiastic. That's something that I remember that I actually also do when I talk to my students. Drinking a beer as it should be. That's also, I think I learned it from Jürgen. And of course, I think that one of the things that I remember is disagreeing in which is the best football team in Mexico. That's the only thing that Jürgen always gets wrong. We all know which one is the best team, but Jürgen gets it wrong all the time when we talk about football. But anyway, I mean, there has to be one bug in the system, right? Perfection is not possible. Then after remembering all this, I was thinking. What could be the best legacy for Jürgen, even if I'm not involved anymore in the experiments that he's working, that I took a different path. And I thought, well, you know, like a father and a son, and in this case, an academic father and a son, I said, well, if I'm about to graduate my first PhD student in January. So what would I like to see from him in the future? That's what I was thinking, and I go again with this independency that Ibrahim was mentioning. Actually, I also told my students that if they ask for a postdoc position in Mexico, I'm not going to write a letter of recommendation. They need to actually move far and do something independent. That's what I told them. So I wanted to share with Jürgen the field that I'm developing in Mexico, the experiments that I brought to the country after finishing my PhD, the international collaborations that I just talked, for example, in the PICO experiment, that's where I am leading the simulations for the experiment. Basically, I have became a Monte Carlo expert for these collaborations. I'm chairing and leading these groups. At DEEP, I have a few students where we are actually doing studies with a non-relativistic effective field theory to set constraints in the experiment, and also combined with other halo substructures. My first PhD student is about to graduate. in the SBC, I'm also responsible for the backgrounds and simulation for this WBS. Basically, that's what I do in the experiments. And of course, I'm also pushing for this proposal to deploy at Laguna Verde or in IN. And at my return to Mexico, this is my lab at the Institute of Physics. I have a few low background detectors at germanium. I have actually 3 germanium detectors and alpha counters. I basically do instrumentation for these neutrino and dark matter detectors. I'm designing a prototype bubble chamber and do gamma spectroscopy and spectrometry with germanium detectors. I'm also pushing to develop the first underground laboratory in Mexico in the state of Hidalgo. So this is very well advanced. We are aiming to start construction this year. Of course, it will be just a 25 square meter hall inside a decommissioned mine in Hidalgo at only 300 meter water equivalent. It's not that depth, but it's still good to do research, prototyping, and environmental radiation. This is one of the test deployments that we did 2 years ago. And of course, I'm pushing for this measurement of neutrinos in Mexico, the first detection of neutrinos, of reactor neutrinos via sevens. And as I said, this is actually the proposal for ININ, 1 megawatt research reactor. We had initial discussions and visit in late 2019, then the pandemic came, but still we got approval to deploy a scintillator detector to measure backgrounds at ININ, and we will start communications with Laguna Verde. And I guess I wanted to share what my academic life has been after I left San Luis Potosí, to show Jürgen that basically I made you proud. And this is actually my research group. This is actually 2 years ago. And this was last week. Actually, we met after 15 months. These are only 2 postdocs and the grad and 5 PhD students. I didn't invite the undergraduates because that's another 6, and 12 people, 13 people. That was too much for a meeting during the pandemic. But this is basically what has been my academic life after my training with Jürgen. So I just want to say, Jürgen, happy birthday. I would like to go to San Luis Potosí and actually have an in-person meeting. I hope that we can do it later this year or next year. And thank you for everything. And that's it. Thanks.
Thank you very much, Eric. Thank you to Professor Eric Vazquez from the UNAM. And thank you for participating in this Jürgen Fest. Okay, we have some minutes for a question. We have around 8 minutes for some question, please.
So I want to first thank Eric for this nice talk, the nice work he is doing. And
Is it me or Jürgen?
I wanted to tell him one thing, one of the thorium lifetime, which you wrote with 2 students at SNOLAB, which demonstrates that the decay rate does not depend on ultrasonic sound or impeding on the nucleus. I'm using it together with a paper from Peter Cooper, which demonstrates that the plutonium reactor on I don't remember the name of the satellite, is independent of the distance from the sun, the decay rate. Yeah, so these 2 papers I use as demonstration that Rutherford is right. Nothing changes the lifetime of particles. Yeah,
yeah.
So I use something of you. Yeah, I have a question. Have you ever heard about liquid krypton detectors for WIMPs?
No. I think that, I mean, we can use helium, neon, xenon, argon. Krypton has, I'm trying to remember that I heard somebody at Princeton or somewhere trying to do some research with crypto, right? But it has some background with crypto, so I think it will be very complicated to do that. But I kind of hits me to have that. We use crypto in deep for calibration, actually, to calibrate the low energy recoils, electron recoils, right? But as a dark matter detector, I think it will be very complicated because I actually don't remember which one. It's a metastable state of crypton. And I see Peter.
Yeah, I'm remembering the same thing, but I can't come up with the details either.
Yes, but because in Na62 we have 70 tons of liquid krypton which are switched on, but only used sparsely. So just thinking, yeah, got the idea during your talk.
Yeah, I guess
somewhere I gotta look.
Yeah, I also hear about that, and the only thing is that that's on surface, right?
Oh no, you're not gonna. You could have the krypton, but you'd have to take it underground to do anything useful with it.
Yeah.
Okay.
If it is on surface, it's impossible, right? Because of the neutrons, right? Cosmic neutrons.
Okay. So another question, please.
Eric.
Okay, I want to read congratulations for Jürgen by Fair RT in the YouTube TV. Okay, and I want to congratulate also to Jürgen for let me participate also as chairman in this 2 sessions. And now I thank you very much, Eric, for your talk again. And now I let the control to Professor Alfredo Mendez. Okay,